Hello everybody, myself Nidhi Gupta. I am assistant professor in Ajay Kumar Garg Engineering College. Today we are going to cover the data structures arrays 1D, 2D and 3D. So let's proceed. So these are the table of contents that we are going to cover. So we'll go for introduction first, then linear arrays. Inside the linear arrays, we go for length of linear arrays, how to calculate the length, array notations, representation of linear array in the memory. Then we go for multidimensional array, that is 2-dimension array. There we go for representation of 2D arrays, representation of 2D arrays in memory, multidimensional arrays, multidimensional array generalized form, and thereafter 3D arrays and operations on linear structure, linear arrays. So let's start with the introduction. So an array is a linear data structure that collects the elements of same data type and stores them in a contiguous memory locations. So we know that the contiguous memory locations is that the memory, the elements are stored one after the another in a contiguous fashion. So the arrays may be stored as 1-dimensional, 2-dimensional or in multi-dimensional form. So suppose this is a array that is given, it is a 1D array, it is having the 1-dimensional, over here 0, 1, 2, 3, 4, 5, 6, these are the index numbers and every element allocate the space inside the memory. So the memory is having the memory address. So 200 is the memory address, similarly 201 is the memory address, 202 is the memory address, and over here we can see, as we have already see that it is stored in a contiguous memory location. So contiguous, you can see that the character, it may take, we are considering the C language, so the character is taking 1 byte of memory. So 200 is the base address, that is a first address, first element address, and thereafter 201 is the next one, 202 is the another one, and it goes on up to the n. Suppose we are having the n elements, then it goes on and on. So we can see that elements are storing in a contiguous memory locations. So this is the just a brief about the 1D array. Now the linear arrays, or we can say the 1D array only. So a linear array is a list of finite number of n homogeneous data elements, that is data elements of same type. Homogeneous means the same type of elements, such that the elements are the arrays, in the elements are of the arrays are referenced respectively by the index number consist of n consecutive numbers, as we have seen in the previous example only. So the elements of the array are stored respectively in successive memory locations. We have already seen in the previous example. Now, how to find the length of the array? So in the data structures, we are focusing on the calculation of the length of the array, how many number of elements are there inside a linear array, or we can say 1D array. So the number n of elements is called the length or size of the array. The index set consists of the integer 0, 1, 2 up to n minus 1, as we have seen in the example earlier also. The index number, we are starting with 0, 1, 2 up to n minus 1. However, it depends on the programming language, whether the programming language is permitting from starting from 0 or it may be any other number. There, for example, MATLAB starts with 1 index number and C starts with 0 index number array. Okay. Now, length or the number of data elements of the array can be obtained from the index set by using this formula, that is length is equals to UB minus LB plus 1. Now, over here the UB signifies the largest index called the upper bound of the array. The largest index number in an array is represented as a UB. Now, LB is the smallest index called the lower bound of the arrays. LB, UB. So, in the last example that we have seen, 0 was the LB. LB, that is a lower bound. And if the array is having from 0 to n minus 1 elements, then n minus 1 would be considered as the UB and 0 is considered as a LB. Now, array notation. So, arrays are represented by different ways by different programming language. Okay. So, elements of an array A can be denoted by, this is one of the way, subscript notation, that is A naught, A1, dot dot up to A n minus 1. Parenthesis notation, A0, 0 is in parenthesis, 0 is the index number, 1 is the index number, n minus up to n minus 1. So, A of 0, A of 1 up to A of n minus 1. Similarly, bracket notation is also there. So, in bracket notation, we can see that A, then we have in the bracket index number 0, 1, 2 up to n minus 1. So, the number k in A of k. So, A is the name of the array. So, A of k is the subscript or an index, and A of k is called the subscripted variable. So, this whole is considered as a subscripted variable. Now, representation of linear arrays in memory. Now, we have already seen in the first example that the arrays are stored in a contiguous memory location. So, over here also we can see that this is the contiguous memory. Over here, these are the addresses. Starting from 1000, 1000 is considered as a base address, and it goes on and on up to over here it is 1005. However, it depends on the number of elements that we are storing. So, this is the computer memory. It is a contiguous, it is storing in a contiguous form. So, representation of linear arrays in memory. Now, let LA be a linear array in the memory of the computer. So, LA is the name of the array. So, LOC of LA of kth element, it means that LOC signifies the address. So, if we are having an array of n elements and we want to know the address of any particular element, then there is a formula for that. So, over here we indicate LOC means the address of LA array at kth position is equal to the address of the element LA of the array LA. Now, the elements of array are stored in a successive memory cell. So, the computer does not need to keep track of the address of every element of LA, because we have seen that the addresses are increasing by its own way. It depends on the number of bytes each element is taking, and it is stored in a contiguous form. So, the computer does not need to keep track of address of each of the element, but need to track only the address of the first element of the array, and it is denoted by base address of LA, that is base of LA. So, the first element, if it is starting from 0, then the 0th element address is called the base address of the linear array. Now, representation of linear arrays in memory. So, LOC of LA of k, the formula is equals to the base address of the array plus W into k minus lower bound, that is LB, that we have discussed in the last slide. So, where W is the number of words per memory cell of the array LA, and W is a size of data type. So if we are storing the characters, so each character is taking 1 byte of memory. So over there the W is equal to 1. So W is the number of words or the number of byte that each memory element takes. So over here there is an example we have seen. In this, the LA is the name of the array. 200 from 200 to 207, this is the memory address, and as we can see in this figure that the index numbers is starting from 1. Okay, so from 1, 2, 3 index number is going on up to 8, and it may go on further also. So 1 is denoting the lower bound, and over here if the array is up to this much element, then the UB is the 8. So the question is that to find the address of the array at 6th position. So the index number is 6. Each element of the array occupy 1 byte. This is given to us. So we will apply this formula, as we have seen this formula, that how to find the address of a linear array. So this is the formula, and we can see that through this calculation we are able to find the formula. Over here we know the base address is given to us. That base address is the starting address, that is 200, plus W. It is being given that it is occupying the 1 byte of memory every time. K is the kth value that we want to find. So we want to find out the 6th index. So 6 is the value of K minus lower bound, that is the starting index. So starting index over here is 1, as we can see from the figure. So it is 1. So it evaluates to 205. So this is example number 1 for finding the address. So similarly, there can be another example. Over here we can see that LA1 is having the 2 byte of memory. So over here W will be equals to 2. So this is the question. Find the address of LA16, array of index number 16 we have to find out, and each element of the array occupy 2 byte of memory. So this is the formula. Again we have applied the formula, and we can see LA16 is equals to 200, that is a base address, plus W. W is the size. We can see it is occupying 2 byte of memory. So W is 2. K is 16, because we have to find the kth index. So kth index means 16th index we want to find out, minus the lower bound, and it is given that the array is starting from 1 index number. So it is evaluated to 230. 230 is the address of 16th index number element. Now this is one of the question you can try at home. Now after this 1D array, similarly there is a multi-dimensional array. So multi-dimensional means more than one. We consider 2-dimension array, 3-dimension array, or more than that, maybe n-dimensional array. So 2-dimensional array, a 2-dimensional array M cross N. M means is a collection of M cross N data elements, matlab means M into N data elements, such that each element is specified by a pair of integer called subscript with the property that the j lies between 1 to m and k lies between 1 to n. So the element of A with first subscript j and the second subscript k will be denoted as A of j comma k. So it means that if we are having the array and we are considering that total number of data elements is m cross n, and at any time we may require to find out the address of the jth row and kth column, then we can denote it like this, A of j k. Now the elements of 2-dimensional array is shown below. So we can see over here how it is stored. The arrays, the two-dimensional arrays is stored in a two-dimensional way. So the first dimension is considered as a row and the second dimension is considered as the column. So A is the name of the array, and in the same way, if we are having in the linear arrays, the array index is starting from 0 to n. Similarly, over here with each element they are associated two index number. The first one is the row and second one is considered as the column. So over here the first element is 0, 0, that is 0th row and 0th column. Second is 0th row, first column, 0th row, second column, 0th row, third column. Similarly, first row, 0th column, first row, first column, first row, second column, and so on up to total A, 2, 3. That is the two index number of the row and 3 index number of the column. So in total we are having the 3 rows starting from the index 0 and total 4 columns are there with us, and both are starting from index number 0. Now this 2D arrays are stored in two ways. This is what we called as row major representation of 2D array, because over here we can see that 0, 0, 0, 1, 0, 2, 0, 3. So the rows 0 is filled first, thereafter we are representing each element, that is this is column first, first row, 0th column, first row, first column. Similarly up to, it goes on and on up to second row, third column index number. This is the rows of the array. These are called rows. Row 0, row 1, row 2. Similarly, these are called the columns. Over here we can see that there are 4 columns in a 2D array. Now, let A be a two-dimensional array. Two-dimensional array having total m number of rows and n number of columns. If you are having m number of rows, it means that and n number of columns, that it means m cross n, that is m into n is the total number of elements that are stored inside the array, two-dimensional array. Let A will be represented in the memory by a block of m cross n sequential memory location. As we know that the array consists of contiguous block of memory, and total memory which is required for storing 2D array is m cross n only, right? So total number of elements is m cross n over here, and so we require m cross n memory locations to store the complete 2D array. So programming language will store the array A either in column by column form or in row by row form. So column by column means one column, then we go for another column, then we fill for another column, and so on. So this is called column major order, and row by row called row major order. So the programming language like Fortran, MATLAB, they go for column by column by default, and in C, C++, Java programming language, we go for by default there is a row by row representation of 2D array. So over here we can see that there is a array, 1D array is there, and this is again a 2D array. Basically it is a contiguous block of memory that is being shown over here. So each memory location is having the 2 index number. One is representing the row, another is representing the column. So over here we can see that 1, 1, 2, 1, 3, 1. It means that the first column in all these 3, we can see that column is first but row is changing. First row, second row, third row. first column, first column, first column. So it means that we have filled the elements column by column. We are filling the column 1 first, thereafter we are filling the column 2, then we are filling the column 3, then we are filling the column 4, like this. So this is called column major order. Over here we can see in this way, we are over here, it is the 1 comma 1 means first row, first column, 1 comma 2 means first row, second column, first row, third column, first row, fourth column. So we are filling the first row first, and thereafter we go for another row, then we go for another row. So we can see over here the row is keeping on changing, whereas the column is fixed. So it is called row major order. Now 2D array, representation of 2D array in the memory. How we can represent a 2D array inside the memory? Let LOC, that we have seen in the linear arrays also. So over here also we are considering that in 2-dimensional we are having 2 index number, row and column. So if we require to find out the location or the address of jth row, kth column of an array named A, then there is a formula for column major order. This is the formula where m comma n, m is the total number of rows and n is the total number of columns which are there in a array, 2D array. And we are interested in finding out the jth row, kth column address. So the formula is equals to the base address of the array plus w into m into k minus lbc plus j minus lbr. Now this lbc is the lower bound of column and lbr is the lower bound of row. Now lower bound of column means that lowest index number of the column. It may happen that every time the as we have seen right now also, sometimes the column is being start from 0, sometimes it is being start from 1. Similarly, there may be any array. Suppose it is given that the column is index number is starting from 32. So and it is ending with 50. So in that case, the lower bound of column would be 32 and upper bound of column would be 50. So similarly, over here also, LBC is representing the lower bound of column and LBR is representing the lower bound of row. Now again we are having the row major order address calculation. So this is equal to the base address of A plus W into N into J minus LBR, K minus LBC. So this is the formula for column major and this is the formula for storing the in row major. So suppose it is given that we are having the C language and we are given with the base address and we are given with the number of elements each address will take, each element will take, and we have given with the n total number of columns and LBR is also given, then we know that C is storing the data in a row major fashion. So we apply this formula and we can calculate the address of jth row and kth column by using this formula. So let's take one example. So consider the array 25 cross 4, array A. Suppose the base address is 200 and W is given as 4. Suppose the programming store 2D array using row major, compute A of 12, 3. So 12, 3 means it is given that 12 is the J and 3 is the K, J, K. So the formula for J, finding the address of J, K is this one. for row major as we have seen. So we just apply 12, 3 where 12 is j and 3 is k. Base address is given to us, that is 200, and w is also given to us 4, and thereafter total number of elements n is given like 25 cross 4. So 25 is the number of rows and 4 is the number of column. So n is representing the column. So we will place 4 over here, and j is given to us 12. Lower bound. So lower bound, if the lower bound is not given, we will consider by default it as 1, and this is again 1. It is by default. So it evaluates to 384. Now, after this 1D and 2D, let's see the multidimensional array. Multidimensional we consider when we are having the more than one dimension. It is a generalized formula. It gives us the generalized formula. It may be 2D, it may be 3D, it may be 4D or 5D or so on. So a n dimensional array, M1 cross M2 cross up to Mn array, B is a collection of M dot M1 dot M2 dot Mn data elements. So if we multiply all these, it gives us the total number of elements, in which each element is specified by a list of n integers such as k1, k2 up to kn, called subscript, with the property that obviously the k1 is in between 1 to m1, k2 is between 1 to m2 and so on. So the element B with subscript k1, k2 up to kn will be denoted by like this or in this way, as we have seen earlier also. So multidimensional array, let C be a n dimensional array. Now we are interested again in finding out the length of dimension. So in the 1D, 2D we have computed the length, that is upper bound minus lower bound plus 1. Using that formula we have seen we can calculate the length of 1D array. So over here also we can use the same formula, but this formula is being used for every dimensions. If we are having total m dimensions, so we will go for L1, L2, L3 up to Lm. So let's see. So Li of dimension I of C is the number of elements in the index set. So Li is equals to upper bound minus lower bound plus 1. So for the given subscript Ki, the effective index Ei for Li is the number of indices preceding Ki in the index set. So for every dimension inside a multi-dimension array, we need to find the effective address for address computation. So effective address is equal to Ki minus Lb. So where Ki is the subscript, Ki is the so the for kth value, for kth index, if we want to find out, then we will from that we will subtract the lower bound to obtain the effective address for that particular dimension. So let's see how we can go for this. So the generalized formula, let's see, address LOC represented by LOC, address of array C having the dimensions k1, k2 up to kn. So we can obtain the address if the element is stored in a column major fashion. So we can obtain the address of k1 to kn by using this formula, and if it is stored in a row major order, then we can use this formula for finding out the address of the array C having k1 to kn index numbers, dimensions. So suppose let's go for the 3-dimension array. So row major order k1, k2, k3. Over here, this is the formula for row major order, that is the base address plus w into E1, that is effective address of first dimension, L2 the length of second dimension plus E2 effective address of second dimension, L3 length of third dimension plus E3. This is a formula for row major. Similarly, there is a formula for column major also. Base address plus W into E3 L2 plus E2 L1 plus E1. So let's consider one example. Given the array A 2:8, this is the first dimension, minus 4:1 is the second dimension, and 6:10 is the third dimension. So it's given that this is a 3D array, and over here for the first dimension 2 is the lower bound of first dimension, 8 is the upper bound of first dimension. Similarly, minus 4 is the lower bound of second dimension, 1 is the upper bound of second dimension. 6 is the lower bound of third dimension, and 10 is the upper bound of third dimension. Now we are interested in calculating the address of A5 minus 1 8. So given that the base address is 200, W is equal to 4, and it is being given that it is stored in a row major order. So the solution is that first of all we will calculate the L1 using the formula upper bound minus lower bound plus 1. So upper bound of first dimension 8, lower bound minus the lower bound of first dimension 2 plus 1. Similarly, lower bound, upper bound is given. So L2 we can find out, L3 we can find out using the same formula, upper bound minus lower bound plus 1. After this, finding the L1, L2 and L3, we'll calculate E1, E2 and E3 using the formula as we have seen in the last slide. So this is the formula for finding out the effective address. So we'll apply this effective address to find out the effective address E1, E2 and E3. Thereafter, we apply the formula as we have discussed right now, and it evaluates us to 628 is the answer. So now the operations on linear arrays. So traversal is one of the operations, insertion, deletion, these are the operations we can see. So traversal, insertion, deletion, search, sort, merging, these are the operations on linear arrays. So let's discuss the brief introduction about these operations. So traversal is processing each element in the array, visiting each element in the array at once. Insertion is adding the new element to the array. Deletion is removing the element from the array. Searching is to find the location of the element with the given value or the record with the given key. And sorting is arranging the elements in the ascending or descending order, and merging is to combine the two arrays in a single array. So in the next lecture we will go for the operations, and thank you for today. Thank you.